Okay, so today we're talking about just polarity, okay, polarity of a molecule. And polar molecules have dipoles, and actually nonpolar molecules have dipoles. Okay, what we're looking for a polar molecule is it's going to have what's called a net dipole force. Okay, and molecular dipoles occur due to unequal sharing of electrons. Okay, and this cartoon is my favorite because it really shows the unequal sharing. Now, obviously, HF only has one bond. So the bond is polar covalent, okay, and you would draw the dipole towards the more electronegative atom, which would be the fluorine, okay, and then you draw the little charges showing that the H is the more positive and the fluorine is more negative. Now, this only has one bond, so you can look at the bond, and if the bond is polar covalent, then the whole molecule is going to be polar. Okay. And in the case of water, same thing. If you were drawing your dipoles in, now this has two bonds. The dipoles will point towards the oxygen, especially also because the oxygen, remember, has two lone pairs on it. So there's a net dipole force. If you were drawing the net in, it would kind of be, if you added them together, it'd be end up going right to those lone pairs. Okay, now this just shows water again. I like putting up different pictures just because I think polarity and the word dipole, it causes a lot of confusion. So I just want you to understand why it's called polarity. You can see here that you have the slightly negative, okay, pole, okay, a negative pole, and then you have a slightly positive pole. Okay, so when you're looking at dipoles, okay, it's two poles. Di means two, and pole. So you have, once again, two dipoles pointing towards the oxygen. Well, that's all right. Now this is what I show honors, and I'm going to correct it for you guys, okay? Because this is in honors, we only do one page of the Vesper sheet, so most of these are true. Okay, in your case, because we're in the second page of the Vesper sheet, some of these points are not always true. Okay, so polar is not symmetrical, and that's pretty much still true. Meaning, and by unsymmetrical, let's just take that to the next level. We're talking that there is a net dipole, okay, or a net dipole moment, we can call it. Now, I teach the honors kids because they get confused that usually there's a lone pair on the center atom, and that's the case for page 1 of your Vesper sheet. However, sometimes the center atom has lone pairs on it that actually cancel each other out. Okay, their dipoles cancel each other out, and it becomes a nonpolar molecule. So I wouldn't really use this one in AP. Okay, and of course, we just mentioned that a polar molecule will have a net dipole or a dipole moment. Nonpolar is symmetrical. I still think that's the case. We're not going to use the lone pair theory because we're talking about a lot of different molecules, and the lone pairs on the center atom can cancel out. And there's no net dipole on the molecule. Okay, so we've kind of corrected our honors theories for AP. Again, just to show you, reiterate the HF molecule. Again, it's a molecule, but it also only has one bond. You could see that there's a net force. Look at the force. Net force to the right. Okay. So this is like the net dipole right here. 12 newtons, which is the force unit if you haven't had physics yet. 12 newtons, 10 units pulling to the left. The net force would be 12 minus 10, which is 2. This right here would be the net dipole. Okay, but they don't cancel each other out completely. This was 12 and 12. Obviously, it would cancel each other completely, and it would be a nonpolar molecule. Okay. I like showing this one for a trigonal planar. to make sure people understand it is nonpolar, and I like showing the scenario with the dogs pulling in equal and opposite directions. Okay, these dipoles also cancel each other out. So if you drew like the dipoles in, there'd be a net one that you would draw for these, kind of like to cancel out if you added them all together. So okay, and this is just showing you some examples of polar versus nonpolar molecules. Okay, most of these would be on your page 1 of the Vesper sheet. Okay, we've got, of course, HCl, which is it's just a linear with 2 different atoms. Obviously, you can see it's not symmetrical. There's a net dipole pointing towards the chlorine. Okay, here's tetrahedral. Okay, 4 bonds, no lone pairs. The equal and opposite forces will cancel each other out. Okay, making it a nonpolar molecule. Okay, here's NH3. Remember, NH3 has a big lone pair on the top here too, which makes it have a real strong net dipole towards that lone pair. Remember, the lone pair has more repulsion capability than a bond group. Okay, and obviously this is polar. This chlorine is drawing a big dipole towards it, being more electronegative than the hydrogen and the carbon. And then we just talked about a trigonal planar with equal and opposite forces canceling each other out. Okay, well, I'm not going to do carbon tetrachloride. We just looked at that. That's a tetrahedral. Okay, we just showed that on this page. It's right there, and equal and opposite forces cancel out. Okay, pH3, you draw it, it's very similar to NH3. Okay, it's a trigonal pyramidal shape. Okay, and because of this lone pair here, got a net dipole pointing towards that lone pair. So this is a nonpolar shape. Nonpolar. This is polar. Okay, TeF4, let's do that one. Te. Te has 6 okay, valence electrons. Let's do the little shortcut. Okay, so remember, it's 6 plus 4 divided by 2. So that's going to be, let me just double check, make sure I'm doing the right one for it. Yeah, fluorine. So that's 5 electron groups, okay? And we only have 4 atoms, so that means it's going to look like this. Te, F, 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 and then I'm just going to do in a different color the lone pair. Okay, and of course there'll be lone pairs on these. Okay. Okay, you can see that, yes, it's got a tetrahedral shape if it didn't have that lone pair, but because it has that lone pair, there's going to be a net dipole. And we have 4 bond groups and 1 lone pair, which makes this one a seesaw. This is one of the ones I got wrong, I think, on that little sporkle. Seesaw. Okay, so this seesaw, because of this lone pair, is a polar molecule. Okay. Now, I just want to make this clear. I like doing this with honors as well. Make sure you understand the difference between bond polarity and molecular polarity. Remember, molecular polarity, you have 2 choices. It could be polar or nonpolar. Okay, and we're looking at the net dipole force. Okay, bond polarity, you're looking at one bond, and it could be polar covalent, nonpolar covalent, or ionic. And you're looking at one bond. Okay, so for example, if I draw carbon tetrachloride, I'm not going to put the lone pairs on the chlorine just because I'm lazy right now. Okay, if you're looking at the whole molecule, okay, the whole thing is nonpolar. Okay, so that's the molecular polarity. If you're looking at the bond polarity, you're going to take one of these bonds. Okay, and when you subtract the electronegativities or look at it where it would be on the chart and make an estimate, you can see that it would be a polar covalent bond. So you can have polar covalent bonds in a nonpolar molecule. Okay, so just keep bond polarity versus molecular polarity clear. Even though all these bonds are polar, because the net dipole forces cancel each other out, it's still a nonpolar molecule. Okay, and then I just want to go back to our other. This is going to be this is our AP. Just to review again, remember a dipole moment is just showing you an uneven electron distribution. Okay, and that's due to differences in electronegativities between two atoms. Okay, but these dipole moments can cancel each other out, which makes a nonpolar molecule. Okay, this is again the same slide we've been going over. In order to cancel out, they have to be equal in size. Okay, so these dipoles have to be equal in size to cancel each other out. You can't have one long one and then a short one. That's not going to cancel out, obviously. Okay, they exist in a molecule that has a symmetrical shape to cancel the dipole moments out. Okay, and these are the shapes, you can look at your Vesper sheet to confirm, that can cancel out dipoles. Linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. Those are the ones that can cancel out dipoles. Okay, again, this is just showing you what we did. We've showed you for a couple days now, just showing you no dipole moment. Okay, showing you a one dipole. Still think it should go the other direction, but and then two dipole moments, but they cancel each other out because they're equal and opposite. And same thing here. This would be a nonpolar molecule down here because these forces are canceling each other out, equal and opposite forces. Okay, to cancel or not to cancel, that is the question. Okay, let's just talk about polar for a minute. All other shaped molecules with polar bonds are overall polar. Okay, anytime an oxygen or nitrogen is bonded to a different element, the molecule will be polar. And here's just showing you water and hydrogen chloride up top. This is showing you electron density. Okay, so the red is where the electrons are, showing you that it's not uniform and that more of the electrons are to the right. Okay, and now what we're going to do is practice. Okay, and let's take a look at, we're not going to do this practice right now, we're going to do the one in on our Canvas page.